I'm going to go to the slides again. Right. So for an inductor, it looks like this circle there on the right. It's a core. This core is a metallic core here on the right, this core here that you see. And what we do, we just turn a lot of wire around it. So copper wire or any conductive wire, silver wire, copper wire, iron or aluminium will work. So you can make your own inductor. And inductors is used for a lot of things. To give you an idea, it can be used for an antenna for your cell phone. Your cell phone has got 2 or 3 antennas. It also has other inductors. So inductor is very similar to a capacitor in that it can store energy for a while. So we can store a magnetic field in inductor and make use of it at a later time. So inductor, the formula for it is here on the left. L is mu naught mu r times area times number of turns squared. This is the number of turns divided by L, which is the length of the inductor. The length here, starting here, it's the circumference of the circle, and that is why I'm beginning of here, I let you calculate the circumference so many times to make sure that you know how the circumference works. So the circumference of this, or the length, equals 2 pi times the radius, or pi times the diameter. So the length of the inductor is the length of this core in length. If this core was a straight core, in other words, a piece of iron that was just long and straight, like 10 centimeters long, like a rod, then the length would be, in that case, 10 centimeters, which is 0.1 meters. Always work this length in meters. So you can turn your own inductor, and in a practical lab, we're going to do that one day. I'm going to show you how to make your own inductor, make use of it to make our own electromagnet. We can make a transformer to make the voltage higher or to make a voltage lower. If you have an AC voltage, we can either make it higher or lower. So the number of turns is important. In this case, it's 1, 2, 3, 4, 5 turns. So for this formula, it will be 5 squared. That will be 25 for n squared. The area that we see there is the cross-sectional area when I cut it through here, and I look from on the inside into it. It will be, in this case, it's around it like a donut, and it will be that cross-sectional area. This cross-sectional area you cannot do in square millimeters. You must convert it to square meters. And remember, there is 10 to the 6 square millimeters in a square meter. Okay. 1 square millimeter, how many square meters is it again? I always ask that in class to sharpen you up. And even today, a lot of people don't know. It is 10 to the minus 6 square meters is a square millimeter. So learn to convert, learn those conversion formulas on page 16 and 17 in the handbook. Now let me talk a little bit about mu naught. Mu naught is the permeability in free air. So it's 4 pi times 10 to the minus 7. So mu naught is this value here, and that is very similar to the capacitor, where we've got E naught and En, and that is the permittivity of the dielectric material between the plates. for a capacitor. For this thing, it is mu naught is the, if it's a ferrite rod, like in this case here, so mu naught will be for free air, but mu r is the relative permittivity, permeability, sorry. So mu naught times mu r. Mu r, I will always give you the relative me, I will always give you in the exam paper. For instance, for iron, mu r is about 1,000. So if this core was made of iron, it'll be about 1,000. If it was made of aluminium, the mu r would be about 5 or 6. If it was plastic, also very small, like 1 or 2. Any metal that's magnetic, like molybdenum or iron or vanadium, those, or nickel, those metals has got a very high permeability. So we can amplify an inductor by putting a core into it. So if I slide the core out of the windings, I got only mu naught, and then mu r becomes 1. In that case, when it's an air core, and I've removed the core from the coil, that gives an air core, and they only have mu naught, 4 pi times 10 to the minus 7. All right, so mu r is the relative permeability, and if I slide it into the core, if it's a rod, like a pen, metal, like a pen or a pencil, but it's made out of metal, I can slide it sort of in and out of the core, of the coil. So in that case, I can amplify the signal or the inductance. I can amplify it by times 10, times 100, times 10,000. It depends on my core. So this gives you a little bit of background about inductors. What we can also do it, we can build a machine to shock someone or to shock the cattle when they go crazy. They use this on a cattle farm, for instance. And you can make a voltage of 10,000 volts. You can also make a Tesla coil, maybe you have it before, where we can generate 1,000,000 volts with a inductor core like this. So I'll get to the formulas for that. Amplify the voltage as well, 1,000,000 times or 1,000 times higher than our 12 volt at lab supply in a lab. So when you make an electromagnet, there's a current flowing through the coil, and we'll get to that as well in the next chapter. But for inductors for now, we will stick with this. And electromagnet is also an inductor. You just take a lot of turns of wire and turn it around the core. So the quicker you switch off this current in the coil, the higher, we call it the back EMF will be, the back voltage will be. I can use a 1.5 volt battery, and I can switch up very fast, and then I can generate 200,000 volts with that. That is amazing. So this is a tool where you can create a lot of different things with. Are there any questions so far? So by the way, this is on page 196 in the handbook. You guys must follow the handbook a bit and read up what I said there.
Thank you, guys.
Okay, the inductance of a coil. I just want to talk a little bit about these three formulas on page 197. The voltage generated by a coil. The voltage, formula here on the left, is voltage equals L divided T. Let's explore what are these units here. So the voltage is basically the back EMF generated over the coil when I stop the current or when I suddenly change it. So L is the inductance. We measure that in Henry. Someone's microphone is on, guys, and they are talking. Just switch it off, please. I don't have time to check on people. I can go now in a list and find you. And please switch off your microphone. I can hear you talking there. You're compromising the whole class because people want to listen to this recording later. This lady is still talking there. Right. So the voltage is L dt. Now L is the inductance. Like I said, we measure it in Henry. Right. Di is the change in current. And dt is the change in time. So if I put a voltage on a coil and I change the current from 1 ampere to 2 ampere, then di will be 2 minus 1, which is 1. If I change the current from 1 ampere to 1000 ampere, then di, the change in current, will be 999. If I change the current from 0 ampere, there's no current in a coil, to 10 ampere, then di, the change in current here, will be 10. So this gives you an idea how this formula works. So L is the inductance. If it was 1 Henry and the current was, the change was 10 ampere, and we do it in 1 second, then the voltage there will be L, the I, which is 1 times 10. So the voltage will be 10 volt that we will generate. It's always a negative voltage. The voltage in this formula specifically is always negative. And so to give you another example, if I've got an inductance of 1 Henry again, which is a fairly large inductor, like my fist, a 1 Henry inductor is about the size of my fist. All right, so if I change the current by 100 amperes, and the time in which I change that, the time period in which I change that current, say that is 1 millisecond. Who can tell me what voltage will I generate now? 100 ampere over a millisecond. See, they are inversely proportional. So therefore, we will generate 100,000 volts. And this is what an inductor is capable. These tasers, which are used for self-defense, the women use it sometimes for self-defense. Those tasers are about 200,000 volts. And if an enemy attacks them, they can shock them. They call it a taser, and this is how it works. It's just got a simple inductor in it, a small penlight battery, a 1.5 volt battery. That's all. It's all you need to generate 200,000 volts. And that's how they make it. All right. So guys, please go and read on 197. This formula is there and it's explained there as well. So the time constant tau for an inductor, tau is L over R. For capacitors, the time constant was RC. Remember RC. So yeah, it's very similar, but for an inductor, it's basically the time constant equals inductance divided by the resistance. So if I have, for example, a 1 Henry inductor, and I've got a 1 ohm resistor in series with it, my tau will be 1 second in this case. This formula is shown on page 201 in the handbook. And then lastly, how much energy can an inductor store? Remember I said we can store energy with inductor. So the energy equals half Li squared. So 0.5 times L. If L was 1 Henry, then it's 1 times the current. And if the current in the above case was 10 ampere, let's calculate the energy. 10 ampere squared gives me 100 ampere. 10 ampere squared, 100 times 1 Henry is 100 joules times 0.5 here. this half there. So it will be 50 joules for our case. Where I gave you an example here on top where I said the current is changing with 10 ampere and depending on the time. If the time was 1 second, then that voltage will generate and it will be so much energy for that voltage. So the energy is really what shocks a person, not really the voltage. You need energy to transfer to the shock machine or to the taser. Right, this formula is on page 205. So inductors in parallel is very much like resistors in parallel. 1 over L is 1 over L1 plus 1 over L2. My formula is my shortcut formula where I say the total inductance is L1 times L2 divided by L1 plus L2. So I use that formula. Inductors in series, you just add them up like resistors. Okay, the inductor charge or rise current, there's a formula on page 202, and my picture didn't show correct here. Okay, there it is. There it is. So let's start on the top there. Very similar to capacitors where we charge up a capacitor with a voltage. We don't charge up an inductor with a voltage. We charge an inductor with a current. There's a big difference. So the charge formula for the charge current, in this case, the current is on this axis, on the vertical axis, and time is on the horizontal axis, just like with capacitors. And we've got this E curve. We call it an exponential curve, which is E to the power T over minus T over tau. So to charge up the current in this inductor, I can use this formula here on the left. So current equals the final voltage, or the final current basically, divided by the resistance. So if I have a 10 volt battery and I calculate the current, it's 10 volt, and a 10 ohm resistor, it's 10 over 10. That gives you an example. What is the maximum current? Is this one here, V over R. It's the one there, that I. We also call it here, that special word that I used, the final current, because it's never a specific value. It's charging up over time, slowly, and charging up, and it never reaches the top here, the final current. So we just call it the current, which is 99.999% of this current. The current, which is V over R. So we use this formula. So the instantaneous current here at this point, any point on the graph, say this point here, halfway, is the final voltage over the resistance times 1 minus E to the minus, well, this is tau, 1 over tau, R over L, but basically it's minus T over tau. Same formula we've used for capacitors. And the structure of formula is just exactly the same, and you do it the same way. And that is why inductors is a little bit easier to teach than capacitors. You've already got the basic formula there. Now, when we discharge the current, when we calculate the discharge current here, after a certain delay, we use this formula. The current is V over R. That is not the final value. Remember, we cannot use the final value here. What you must use is the value which you used to charge it up. Say it was, in that case, 1 ampere. Oh, I've lost my place now. Sorry, guys. Can you still see the slides?
Yes, we can.
Yes, sir.
Okay. I clicked with my mouse and suddenly it disappears. But I just want to show you, remember mu naught that I talked about in inductor, this number. Mu naught is 4 pi times 10 to the minus 7. Henry per meter is the unit. You must know the unit. So mu naught is in free air without any core there. So the inductor has only got a wire winding. We call it an air core inductor. So in that case, mu naught, the permeability is this value here. However, when I've got a metal ring, iron or any other metal here, then we also have an extra mu r, the relative permeability. That is mu over mu naught. But I will give you this value, like I said here on top, if you read here on top, since for ferromagnetic materials, it is 1000 or more. So the mu relative permeability of metal is about 1000 or more. And I will always tell you in exam what is the value. But this one you must know for free air. I'll skip these slides because it's your next chapter. I'm not doing that chapter now. So we will calculate the reluctance like you see here and so forth, and very complicated formulas. Once I've teach you, it's not so complicated, so don't worry right now about this. So here's the inductor again, and there is mu naught and mu r used, those two values that I showed you now, to calculate the inductance of this inductor. So let me get to my formula again. So again, for the instantaneous current and the delay, that voltage over R will be basically the voltage that you had over the inductor at this point after charging it, say, to half the value, and then you're discharging it. So we won't use the final value here, this V over R. It is the value at the inductor after this time. We begin with that. Plug it into the formula, times e to the minus t over tau. You can look at page 202 for that formula. It's easy, and look in a book. So we try to follow the book, and I actually work out of the book. That's why I give you these page numbers. These slides is also on Brightspace. I'm not sure if anyone went to look at the slides. Okay, basically, this is all the information about inductors. So I just want to start with this magnetic fields as well, and just do an introduction to that. So a magnetic field is defined by these three basic concepts. A current carrying wire produces a magnetic field in the area around it. That's just how an antenna works. Also a coil, like this inductor we talked about now, or a solenoid. We sometimes call it a solenoid or a coil, and or an inductor. So basically, the current flowing through that inductor will create a magnetic field around it. People, that field reaches very, very far. The field goes to, when you switch on an inductor, and you put a voltage over an inductor, I just want to tell you this, that field goes through all the people in the earth, through their bodies. It goes through all the animals in the earth. That field, even of that small inductor that you are powering up, also goes through the sun and the moon. It takes 8 minutes to reach them, but it goes right through them and around them. And it goes to the stars forever and ever and ever. And the curve that it follows is that E curve that I showed you for the inductor, the charge curve. It follows that curve. And in a million years, this signal will still carry on flying and flying, and it will never reach the top value of the inductor, the final value. Now, that is very interesting. So all the phone calls that you call now on your phone can be heard in a million years. The signals are still flying. They never ever stop. They become smaller and smaller, but they never stop. So that is how we can look at the stars and record the magnetic fields and see what happened on the stars like a zillion years ago. That's how they do it. Now, if I move a wire next to that magnet, I will generate a voltage. And this is how your little motors work, your little generators for your projects. It works on this principle 2. So that motor becomes a generator and it will generate a voltage and a current. Now, if I'm a current carrying wire, if I have a current in my wire and I'm put it close to a magnetic field, then that wire will start moving and it will make a motor. And that's how what causes a motor to work. It's basically these moving magnetic fields. Right. So the next slide, I'm going a little bit upside down, I know, but I just want to introduce you to this. The magnetic motor force is measured in ampere, and we call it the MMF. The SI unit is ampere. The flux inside an inductor. There's a flux that flows in it. The magnetic flux flows in it. It's not sitting still, it's moving all the time. And we measure that in Weber. The SI unit is Weber. So it's usually milliweber, so it's about, usually the flux in an electromagnet is about 3 to 5 milliweber. The magnetic field strength, H, is how strong is the magnetic field of that inductor. So we measure that ampere turns per meter. Magnetic flux density is how dense the flux is, because we can compress the flux to a very dense area, or we can uncompress it to a very not dense area too. So we measure this flux density in Tesla. So the relative ability, mu r, we've talked about it. Relative ability is about 1,000, so there is no units for that. The reason is because it's mu divided by mu naught will give you this value. So there's no unit for that one. So if I say the relative permeability of iron is 1,000, there's no units for that. So mu naught is the permeability of free air or of a vacuum. And usually wood and plastics also, they are very close to mu naught. It's a millionth of the value. So it's about 1 millionth of the henries per meter value. So mu naught we measure in henries per meter there. And it's 4 pi times 10 to the minus 7. You must know this constant. It's a constant and it never changes. Well, it changes slightly with temperature and so on. Right, reluctance S is how reluctant is a magnetic material to accept a magnetic signal. So it's sort of like a resistance. It's a resistant like a resistor. Very similar, the reluctance is very similar to resistance. So where the flux flows in a magnetic core, this is how the current flows in a resistive circuit. So you can compare it with an electric circuit, this reluctance. Inductance we already talked about, and we measure that in Henry. So the next one, let's talk about the magnetomotive force. The magnetomotive force is Ni ampere. Now if we look at the picture, it's basically a coil, the blue coil here, of one wire, one winding. The number of turns here is 1. So N will be a 1 here. So the MMF is N, which is 1, times the current flowing through that wire in ampere. If it's 1 ampere, then the MMF is N times 1, which is 1 ampere. People, there's a microphone going on again. Please switch it off.
Sir.
Recording this. Now the number of lines that you see here, do you see 1, 2, 3, 4 lines? The number of lines. That is the flux line, so we call that the flux. The flux is, in this case, 4 Weber, because there's 4 lines. If I have a big magnetic field and there's 10 lines, the flux will be 10 Weber. That gives you an idea how that works. Okay, so I just want to go to the next slide. And in the next slide, we can see mu naught is 4 pi times 10 to the minus 7 Henry per meter. And this is for an air core of a coil in free air or in vacuum, and there's no magnetic core close to it. And that's the only value we use. Mu relative is mu over mu naught. And in that case, whatever the material is, I will give you that. For iron, it's about 1,000. So this is the last page where I'm going to stop with this recording. And I just want to introduce you to this formula. Now, H is the effort that current is putting to produce a magnetic field with a flux flowing inside. So the flux will flow like my mouse cursor in here. People, can you see my mouse cursor? Please respond to me. Yes. Can you see this mouse cursor? I want to make sure you can see it. Otherwise, yes. I can't explain, guys. You can see it. Thank you. So the flux will flow here, and that is phi. You see that phi sign there? The flux is called phi. That's phi. The Greek phi for F. That's F in Greek. So the flux is phi, and it flows in this direction here. It's like a current flowing through a resistor, but it's different. It's magnetic current, sort of. It's a magnetic current flowing into that metal, and that is why we call it flux. So the current is I in this direction, so there's a coil wound around this metal core, maybe 8 turns, 1, 2, 3, 4, 5. There's 6 turns here, so the number of turns, N, is 6 in this case. So magnetic field strength H, we're going to calculate that for this magnetic circuit. The magnetic field strength H equals Ni. Number of turns, which is 6, times the current I. Say it's 1 ampere. So H is Ni. So it's 7 times 1 is 7, divided by the length. So the mean length is also IC. We call it the circumference. LC, sorry, that's an L. So this length where the flux flows here, that average length is the length of the core. It's the circumference of the core. We don't take it on the outside like you've learned in school. We never do that. We take it right in the middle, the average circumference. To get the average circumference, what I always do, I take this length minus the inner length there. I divide it by 2. Then I've got this distance on top and this distance on the bottom. So if this is 10 centimeter, this length, and that is 8 centimeter, that length of the inside, 8 centimeter. I subtracted 2. 10 minus 8 is 2 centimeter. those 2 centimeters is left for this height and that height. That's how you get the size of the core here. So to get the average flux will flow between 10 and 8. So the average flux, I'll take that length there, in which case it's 1 centimeter on top and 1 centimeter on the bottom. So the middle of that 1 centimeter is 0.5 centimeter. So I again divide it by 2. And this 1 centimeter here, 0.5 centimeter bottom, 0.5. So if I want to calculate the average length, this is how I do it. The average height now. It's from here to there, which is 8 centimeters plus 0.5 plus 0.5, which gives me 9 centimeters. So the flux circumference will, from the top to bottom, be from there to the 9 centimeters. People ask me, is there anyone that's unclear about how to calculate the circumference? That is for the height. The width we do the same. Say for instance, this is 20 centimeters from left to right. 20 centimeters outer distance, né? And the inner distance is 18 centimeters. So to get this thickness here, I say 20 centimeters minus 18 is 2 centimeters. Divide by 2, so I know this is half centimeter here and half centimeter there. Also, when I calculate the cross-sectional area here of that area there, I need this distance and I need that distance. So in this case, it will be 1 centimeter here and 1 centimeter there because this is a square. So to calculate the cross-sectional area, it's 1 centimeter by 1 centimeter. How much is that in square meters? Does anyone know? 1 centimeter times how much? 10 to the minus what? 3 or what? Can anybody answer me about this?
Minus 3.
1 centimeter, 1 centimeter. People, calculate for me how many square meters will that cross-sectional area be? Anyone can answer?
To the 10 to the power 6.
No, that is 4
In square.
millimeter, okay? That's 4 millimeter. Remember, we've got a centimeter, which is 10 millimeter by 10 millimeter, right? Which is 100 square millimeters. In your book on page 17, guys, the answer is there. Look in your books. The table is there. To convert a square centimeter to a square meter, you've done it in school, somewhere in standard 6 or standard 7. I don't know what grade that is. That's when I've done it. So a square centimeter is 10 to the minus 4. Minus 4 square meters. Now I'm surprising everyone. I'm continually surprising you. Yet you've done it in school, you've just forgot the conversion factor. Please learn it again. Please catch up, guys, there on page 16 and 17 in the handbook. It tells you the conversion factors. Millimeter to meter and square millimeter to square meter and square centimeter to square meter. So guys, you must please learn those things. It's in exam. It's really an exam tip that I'm giving you. All right, I want to stop here with the slides. And do you guys want an example or two to calculate?
Yes, please.
Let's see if I got a nice example for you. All right. I'm not going to give you the whole example because it's a bit complicated, but I'm going to give you this example here. And I'm going to give you 5 minutes. And I want you to just calculate the MMF of the score. How much is that? What is the MMF? Who can tell me what that is? Guys, it's so simple. You'll kick yourself if you know. Read the board, I always say. It's written on the board. What is the MMF? Magnetic force. Yes? Yeah, tell us. If you can read, you can tell us, please.
100 amps.
You are so clever. It just shows you no one else can read in this class. Guys, I've done it for you. I said read the board. What I meant, the MMF is here. It's N times I. Now N is 100 and the current is 1 ampere. You see there. The magnetic force is 100 times 1 ampere, which is 100 amp. The MMF we also measure in 100 ampere. Very similar to, because it's still a current, just like the current with a battery and a resistor. Right. So what is the magnetic field strength here? H. Please, can you guys calculate that? I'll just look at a board, guys, do it and explain to me how you got to the answer. What is the magnetic field strength for this magnetic circuit? Anyone? Just try. What's the magnetic field strength? H, people. What is the magnetic field strength? H. Read here. If you can't do it, what is it? Can someone try again? That person that answered me, just answer again. What is it here? H is MMF over the length. And I said, I told you the length is 40 centimeters. Do you see 40 centimeters?
Yes, divide by 100.
Yeah, MMF is 100. Eh? There was an MMF of 100 and a length of 0.4 meters because that's 40 centimeters. That value there, right? So we will have 100 divided by 0.4. And that is why it's 250 ampere per meter. I'm not going to ask you the next two because I haven't done this formulas with you. I'll do it later in the week. We can do another class. Right, let's see if I've got another example. There is a nice example. It says calculate the total reluctance. I'm not going to ask that. I'm going to tell you. If the current is 1 ampere, then you must calculate for me what is the MMF. What is the MMF in this case? The current is 1 ampere, people. So MMF is N times I.
Which is 400.
400.
How much? No, thank you very much. It's so simple, but I need you to do it because people, this is very important. Listening to me doesn't grow your brain cells really, but doing the problem on paper, that actually you're practicing your brain cells to expand and grow. So it's very good for you to do actual practicing. That's how it works. What you can see in this, sorry?
1000 ampere per meter.
Yeah, the magnetic field strength is
Yes.
Ni over length, né? And the length is again 0.4 meter, né?
Yes.
You guys see how to do that?
Comrade Fred, please, I'm the CEO of Izaka. Can you please?
Right.
Comrade,